In this video, we'll begin our discussion of the Excel trend curve. The Excel trend curve can be used to fit various equations to data. So what's the first thing you should do when you want to figure out how two variables are related? Well, you should plot them. And so you plot on the x-axis the column to the left of what goes on the y-axis, the column to the right. Here are some examples. You might want to predict monthly costs from units made. You might want to predict the price of a home from the square feet in the home. You might want to predict the return on a stock from the market return in that month. You might want to predict the company's total sales from ad expense. In each case, you should graph the independent variable, as we call it, the x variable, put that on the x-axis, so it should be in a column to the left of the dependent variable, which is what you want to predict. So let's look at an example of how the trend curve works. So we have 14 months of data for a company. We have the units produced, let's suppose they're refrigerators, and the monthly cost of running the plant. There should be a relationship. The more units that are produced, the higher the cost of running the plant. So we want to get some insights into the form of that relationship. We should graph these points. So we select the data, including the headings, and you do scatter plot. Please don't do a line plot. The scatter plot is right here. So you do a scatter plot, and we'll just have the dots there. Okay, now if we take a look at this, it looks like a straight line should fit this data. On the x-axis is units made, y-axis is total cost of running the plant. It looks like there should be a straight line going right through those points. Now we can find that with the trend curve. We select all the points, and then if we right click, you'll see add trend line. And there's a bunch of choices, which we're not going to do all of these in our module, but we're going to do exponential, power, and moving average, as well as linear. Logarithmic's not that big a deal. Polynomial is not that important either. But it looks like a straight line would fit the data, so we click on linear, which is the default, and then we could say display equation in R squared, and then we'll explain what we get there. So we display equation in R squared. Now we should probably make this a little bit bigger. If we would select this, I can do Control 1, and I can pick a bigger font, so we can see this a little better. Okay, now you can see the line that sort of splits those points in half. That's called the least squares line. It minimizes the sum of the square distances of the points to the line, sort of splits the points in half. The distance of the points above the line and below the line are equals. We'll see in a couple of minutes. So it says here your best bet at predicting the cost of running the plant is 37,894 plus 64.269 times X, which is the units made. Now that 64.269 is basically your unit cost. Every extra unit you make costs about that much money, and this is your fixed cost. The R squared of 0.6882, R squared is always between 0 and 1, tells you that 69% of the variation in monthly cost, your dependent variable, is explained by variation in your units produced. Okay, now can we put in our spreadsheet what the predicted cost would be for every month? In other words, make this prediction equation operative. Well, we would take equal the slope, 64.269 times the units made, and add that 37,894. More decimal points would be more accurate, but we won't worry about that. So that's your predicted cost. Double click the left mouse to copy it down. It goes down a bit too far. So we now have a prediction for basically each of those months, for basically what the cost of producing the number of units would be. We have the actual cost. So what's the error? Actual minus predicted. Let's take the actual cost minus the predicted cost, and that measures how far the point is above or below the line. So that first point's about 4,000 units above the line. Now, if I copy that down, I have the errors, and the sum of the errors should be approximately 0. Let's see if that's true, because the line splits the points in half. So I add up those errors, get minus 2.04. Now that would be exactly 0 if I added more decimal points to this equation, but I'm not going to worry about that. Okay, now the information we got in the chart could actually be obtained from Excel functions. There's a slope function to get that slope, an intercept function to get that intercept, an R squared function to get the R squared value. And as to the accuracy of these forecasts, there's an STEYX function that will show you, and 95% of your predictions should be accurate within 2 STEYX is. So let's quickly go through those. So now we can name these ranges of data. It'll be easier for us. Select the data, go formulas, create from selection, name in top row. So we've named this column units produced and the next column monthly plant cost. So how could we recreate that slope? Well, guess what? The function's called slope. So say slope, and what comes first is the Y range, which is monthly plant cost. And then what comes next is units produced right there. So that says, what's the slope if you predict monthly cost from units produced? 64.2687. That's where more decimal points would help. What's the intercept? That's the constant term. So I would go Y first, monthly cost. Just double click with autocomplete. Units produced. And I should duplicate that 37894. And I do. What's the R squared? The function for that is RSQ. R squared, the Y coordinate would be monthly cost, the Y variable, and then units produced. And it doesn't matter what goes first there, X or Y, R squared will come out the same. But there's your 68.82. Finally, the standard error of the regression, STEYX, and the Y values are in the monthly cost column, monthly plant cost, and the X values are in the units produced column. This will come out about 13,700. Okay, now what does that mean? 68% of our forecast should be accurate within one standard error of the regression, 95% within two standard errors. So an outlier would be anything that's a point where the prediction's off by more than double that 13,771, or about 27,000. We have no errors that large, so there are no outliers. Not a good or bad thing, just a fact. But we should really understand, again, normal variation. Even though in this month here, the actual cost was 20,000 higher than we expected, that wasn't an outlier. It was normal variation. Now, what we should really do is learn from our outliers. Months in which we did much better than average, costs were much lower than predicted, we should basically try and replicate those months, and months in which our cost was more than two standard errors above predicted, we should try and find out why that happened and make sure that never happens again. We'll see in the next two video situations where fitting a straight line would not make sense. So in our next video, we'll look at exponential growth, which is what you should use to fit a curve usually when the curve gets steeper.